Morning, everyone. So yesterday we started taking a look at errors in chemistry. Errors are the conversation is around accuracy and precision. Basically, there is a true value that we're always looking for. When I make an experimental measurement, the closer that I get to that true value, the closer I get to the bullseye, the more accurate I am, the more valid my measurement. In science, we also want results to be reproducible and repeatable. So if I throw that dart here multiple times, I can say that something is more precise. If it wasn't by chance that I landed in the same position, but I seemingly am getting the same values multiple times, I would be a very precise measurement. Although be careful, sometimes we are very precise, but actually not accurate. The two reasons why errors show up, the main categories are random error and systematic error. You're going to find on all of our labs, there's going to be a question, where are places that random error showed up, where are places that systematic error showed up. For random errors, think about it as an equal chance of being a little bit higher, a little bit lower. It could be unpredictable fluctuations just in the device or our limitations in reading the scales that we have. Or systematic errors are more so something is flawed with your design, something is flawed with your procedure. In that case there, you need to, depending on what the issue is, redesign the experiment. So do practice using that terminology here. It's good to identify things as random or systematic. Today what we're going to introduce here is carrying through the math here. First thing, how do we represent the errors in these numbers? And especially when I start crunching through the numbers, plus and minus, multiply and divide, how do the plus or minus, these error bars here, actually carry through the problem? So for starters, before we get to that math here, I just want to show you there's three common ways of showing error. Let's call this A here. We'll call this one here absolute error. This is the most common way of doing it. And absolute error is quoted in the same unit as measurement. So you go to take down a reading for something, let's say for example, let's say we had a test tube, let's say there's a 100 mark here, let's say it is water in the background. I go around and ask a few people, well, how much is in there, right? You might say to me, oh, I think 40. Some people might say 40, 41, 50, 30, 33, 37, right? At first, I would be scratching my head and I'd be like, well, we are looking at the same container, right? Well, again, just like yesterday, this tool here isn't very precise. It is a graduated cylinder, but it doesn't have all the graduations, all the markings I would expect. When I read the bottom of the meniscus, just based on my own interpretation and the limitation on the apparatus, there is a little bit of fluctuation. So what I would do here is I would actually just write down some number. I'm going to write down the number. I'm seemingly getting like the 40s a lot, so maybe I'm going to say 40. But because I do get up to a 50 and some of the 30s, maybe I might say plus or minus 10. Right. This plus or minus part here is known as the error. We'll talk about how do you decide how big the error you need is, but pretty much at this moment here, you wanted to capture some of the extremes. We've done these repeat trials here to try to minimize these impacts of the error. We still are saying, I'm thinking it's 40, but just in case I'm wrong, I might be upwards 40 plus 10, which is 50, or 40 minus 10, which is 30. You're going to find sometimes when you associate this error here, sometimes it may not capture exactly the error, but you do want the plus or minus to be large enough to hopefully get close to it. In terms of units, you could, in this case, it's going to be milliliters of solution. It would have been 40 milliliters plus or minus 10 milliliters. In chemistry here, we're just going to leave the units on the other side. So in this case here, the absolute error is this plus or minus part. It gives me a little bit of buffer room, a little bit of room to be wrong on either side. We usually throw around a number like, I'm 97% confident. It's at least going to be that. It's totally possible. I mentioned the silly example yesterday. Oh, what if the manufacturer came back to you and said, whoops, really sorry. I meant to say that this is 10 milliliters. We'd say, great, thanks, right? Where I was saying all the 40s and 30s and 50s, I really meant to say 4s and 5s and 3s. So even with this error here, I might still be wrong, but that's something more a systematic issue. What I'm sort of thinking here when I actually plot this here back to our, let's pretend it actually is 100. We're guessing it's 40. So sort of, I know where the 40 mark is, and sort of if I plotted my level of confidence, I'm making the measurement, I think it's about 40. Like even there's a little bit of random error, there's a random skipping up and down, but it should be about 40. But just in case I'm wrong, I'm letting my confidence drop off. It shouldn't be anywhere sort of past 50. It shouldn't be anywhere past 30 here. In that case there, this plus or minus is going to be equal chance of being right or wrong, you see that that plus or minus is actually an indication of random error. So that's an indication of just fluctuations. It could be wrong on either side. I'm not expecting it to be far off what the real mark is. What if they came back and instead of switching it to 10, what if they changed it to 1,000? Okay, all these manufacturers I wouldn't order from anymore. But if really it's 1,000, I had given myself this buffer room and I realized, oh, I'm still wrong, right? In that case there, maybe the true value, the valid answer is way over here at 1,000. In that case there, my random error, which is equal chance plus or minus being up or down, in that case there, it doesn't really cover the true value. Anytime my true value, sometimes you call the true value the literature value, it's the value that's in the books, it's the value that you reference to. In that case there, this would be a deviation all in one direction, and that deviation there would be more so a systematic error. So something was wrong, in this case here, it was wrong with your equipment, it was wrong with them to just say 100 when they meant to say 1,000, and that's why all your values are skewed all too tiny. What we're going to see when we do this section here in chemistry, so looking at these numbers here, I'm going to be looking for error. Because error is a sort of rough buffer on either side, this is how wrong I could be on either side, there's no sense of being overly precise on that side. So for example, if my measurement here was guessing, I think it's 40, but my buffer, my error I'm going to leave it is actually 11.2675432. My question would be, well, why be so precise with this? If it is already going to be a slight range, if it just gives me some sense of how your confidence is going to drop off on either side, you don't need this to be very precise. So we're going to find in chemistry, at least when we write out our numbers, we're going to always be rounding. So round errors just to 1 sig fig. Right? There's no reason to be overly precise, right? So this to 1 sig fig, if I'm allowed to only keep one digit, I'm keeping that one there, so I can say 40 plus or minus 10. Right? If I'm really not confident, oh, it's not within 10 though, I do maybe plus or minus 20. But in the same vein here, there's no reason to be overly precise. There's no reason to keep all these other decimals here. So one significant figure for the error. And now here's the thing is, if the error right now here, let's take the error as 20, what we're going to be looking for is your measurement. This one here I'm calling your measurement. This is what I'm taking down the reading is. This is where I can actually read sig figs, right? How precise, how many digits am I keeping? This part here is what I'm calling the error. In this case here, it's the random form of error because it's plus or minus. What I'm be looking for is the position where your error is should line up with the guess on your measurement. So in this case here, I'm guessing it could be in the tens place. It could be off by plus 10, plus 20. But I'm noticing that on the guess, this number 40 is also one sig fig number. If the one and only digit I've given you is also a guess, notice my guess is in the same position as that. Why is that important? In this case here, if the guess with a number like 40, I'm saying, well, this 40 could be wrong. This is sort of an estimate value here. I'm just eyeballing that value. Maybe this one here is actually 60. Maybe it's actually 70, right? I'm actually showing you that the precision is actually off at the tens position. That lines up well with this 20. When does it not line up well? So let's say I had another measurement. What if I was guessing 45 plus or minus 20? I wouldn't be surprised if you see in your textbooks it written like that. But at least in chemistry here, something's off. Because when I look at a number like 45, I notice that this number here has 2 sig figs. The last number is going to be my guess. This says, no, I'm actually sure of the 40. Where I might be fluctuating is maybe I'm talking 46 or 47 or down to 42, 43 or whatever. That doesn't jive really well with the error. Well, if this error here could actually be in the 50s or 60s, it really should mean I'm not actually confident here. So if this showed up in our calculations later on, if the error has to be in the tens position, I would round this. Maybe I make it 50 plus or minus 20. So therefore, my guessed position, where I'm actually guessing my measurement, right now it's in the tens position. It lines up with the tens position of the error. Exactly the opposite problem in the other case here. What if I had a measurement here? What if I had, back to my 40, but what if I had a smaller error, let's say plus or minus 5? It's good. My error is 1 sig fig. But this time my error is unsure. The buffer is in the ones position. When I look at a measurement like 40, my one and only number, the 4 here that I'm not sure about, is actually unsure at the tens. So this still says it could be 50, it could be 30, it could be 20 and whatever. Then that doesn't jive well with the fact that your confidence only drops off 5 on either side. Shouldn't the error be at least 10? So in that case there, I would, if this is the case, I would then round it maybe 40 plus or minus 10. Even if this error here, we'll see some strange cases here, even in this error here with 3, so sort of same problem, the 1s doesn't line up with the 10s place. You don't want to do your regular rounding because this 3 here is less than 5, it would drop to 0. We don't suddenly have no error. It's always better to round the error bigger. Because graphically what we're saying here is if you would have fit in a plus or minus 3, if I have to round it upwards, instead of rounding out to 0, which is the closer value, if I have to round it to plus or minus 10, at least what would have fit in plus or minus 3 would definitely fit in plus or minus 10. Now that sort of begs the question, well, why don't I make errors infinitely big? I am still trying to make a good reading. I'm still trying to tell you this is my measurement, and here's just a buffer region. How far might I be wrong? In general, I want to keep the errors as tiny as I can get them. Obviously, my reading is going to fit within plus or minus 1,000, but that's not actually going to give me any important measurement. So, a couple key things from this section. Again, there's no point in keeping our errors to way too many digits. We're going to be rounding our errors just to one significant figure, and then we're going to make sure wherever we're guessing that error position, it lines up with the guess on the measurement. In this case here, is a number like 2340 plus or minus 20 okay? Notice that we're not matching up sig figs. We're not saying, well, if error has to be 1 sig fig, this has to be 1 sig fig. In fact, 2340 actually has 3 sig figs. That's fine. With a 3 sig fig number, I'm sure the 2, sure the 3. It's just that my guess, with the very last one, the one that's rightmost, has to be lined up with the error position. That's what I'm going to be looking for, and I'm going to read that here. The uncertainty, where you're actually guessing, where I might be wrong. If you came back and told me 2350, 2360, I'm not surprised. I had eyeballed that value anyways. The uncertainty must line up with the error position. So not the sig figs. It's not error is 1 sig fig, your measurement is 1 sig fig. In this case here, my measurement is 3, that's fine. But where my guess is actually 10's position, 10's position. It's still an absolute error though. Absolute error is this plus or minus part. We had done sig figs for our measurements, but we're doing error for this plus or minus part. Units come at the really end. This is the absolute error. Maybe this was a mass, so I can go grams just directly at the end. So that's the most common way we're going to be practicing that through the math. Second way we can talk about error here is something called a relative error. Relative error can sometimes be called as a fractional error. I'm going to try to avoid the language of percent error because percent error is something different, and I'm going to come up to that in the next one. So relative error here, let me just give you the formula. It is taking this absolute error and then dividing our measurement. But given that it is a fraction, it is sort of relative to something, it is still going to be a percentage. Right? Weird enough, I'm not going to call it percent error. But let me just show you what I'm talking about here in calculating the relative error. Let's say I make up a number, let's say 5 plus or minus 1 milliliter. First, double check if that's okay. Is the error 1 sig fig? Yes. Is the error rounded to the same position as my guess? Yes. Both of them are in the ones place, so this is good. This case here, we can call our absolute error. Essentially, what relative error does for us here is it actually helps us figuring out how bad is your absolute error on your measurement. So in this case here, my absolute error is 1. I'm not going to worry about the plus or minus. I know it could have been either side. If I have a 1 out of a measurement that's 5, because the 5 is actually a fairly small number, that gives you 0.2. You multiply it by 100, and we get here a 20% relative error. So not percent error, but we're 20% off the mark. Because I'm giving myself room to be wrong 1 on either side, because the 5 wasn't also big, it's going to be 20% relative on either side. What if I was using that exact same grad cylinder, and what if this time I take the measurement and I actually have more liquid in the grad cylinder? Maybe it's 50. I do that annoying thing with the decimal just to make sure that it lines up properly. In this case here, oh, my measurement actually has 2 sig figs, that's fine. The guess is in the same position as the error. That's what I was looking for. In this case here, this is typically the case. Usually your apparatus always gives you the same error. So the apparatus is giving me plus or minus 1. That's how detailed the tick marks are. However, in this case here, because the measurement is a lot bigger, I'm measuring more liquid. If I have a 1 out of 50, I end up seeing, well, that 1 isn't as bad anymore. This is now only a 2% relative error on either side. So we'll just write down in words here. Although when we talk about absolute error, although we have the same absolute error, it was a plus or minus 1 on either measurement. We make the conclusion here, bigger measurements. So if I measure more liquid, bigger measurements are easier to read, and we see that here it has a smaller relative error. Another way of saying that here is, I know it's a plus or minus 1 on both of these measurements. How bad is my plus or minus 1? When plus or minus 1 is on 5, it's 20% bad. When the measurement itself is a little bit larger, it's a little bit easier to see more liquid. So if I have the same plus or minus 1 acting on 50, it's only 2% bad. So I've been trying to avoid that terminology here, percent error here. Percent error is actually something totally different. You will be asked in some labs here to calculate percent error or percentage error. And in fact, percentage error is not so much to do with absolute error at all. Percent error is more a comment on the accuracy that we talked about yesterday. For percent error, again, I'm going to give you the formula. We're going to take our measurement, take what we believe our reading to be. We're going to minus off the accepted value, also called the true value or the real value, the valid answer. And what I'm going to do is I'm going to divide it by the accepted or divide it by the true. This one here is going to be just it's a percent error. I'm this percent too high or too low, so we're going to put an absolute error. And in this case here, you're just going to take the number without the plus or minus. So yesterday we did this example of just counting students in the classroom. Let's say the true value is there's actually 28 students in the classroom. Let's say when I go ask a person, they end up saying, oh, 25 students, 24 students, 25 students, right? So in this case here, I can comment, well, they're not very accurate, right? They didn't actually get close to that true value, 28. But when I asked this person a couple times when they did those repeat trials, they actually do have high precision because there's a consistent reading. If I ask this person again, I'm guessing they're going to guess something like 24 or 25 again. It wasn't by chance. So if I were looking at this, right, making those repeat trials here should be limiting the random error. I might guess, oh, maybe 25 students plus or minus 1. Again, check that your error has one sig fig. Check that it's lined up. Perfect. Everything is good. And then my units, in this case here, would be students just afterwards. In this case here, I'm just going to plot this out graphically here. I was supposed to say 28. 28 was the real value. When I take a look at my measurement, when this person had actually given you the number of students, he said 25. I know he's off. Right? This part here shows me the inaccuracy. It shows me sort of how far off he is. And when he gave himself an absolute error of plus or minus, he was most confident in being 25. He let this confidence drop off, one on either side, maybe 26, maybe 24. Shouldn't be any more than 26, shouldn't be any less than 24. Little did he know, he didn't sort of look at the classroom. Maybe he missed a complete side of the classroom. He always missed counting the same few students, which is why precisely he is still giving the same number, but it's off. In this case here, when we're actually talking about percent error, it is talking about how far off the mark he is. That's what most people do. The most common problem I see here is people tend to just do measurement divided by the true value. I'm not just saying 25 divided by 28. What I want to know is I actually want to know how far off the mark he is. So if he said 25 and the true value is 28, how far off he is only 3. He's not off by 25. If you know that 3 there, again, we're going to take an absolute value, so I know it's just going to be 3 on the low side. What if I took 3 divided by 28 in this question here? What is his actual percent error? Again, this is a comment on his accuracy. He is about 11% off the mark. In this case here, it was negative, so I can say in words here, he's 11% below the true value. And using your judgment here, there's no sense in making this percent error all too precise. So if my calculator had given me, I think it's at 10.714, right, just round it to something that's reasonable. Okay, I'm 11%. I took the absolute value, so I don't need to worry about positives or negatives. You'll notice I also didn't factor in the plus or minus 1 at all, right? I just took the 25 directly and I said, well, 25 is 3 off the mark. What's 3 out of 28? How bad is that? And that's your accuracy, 11% on the low side. This would, again, be an indication that something is systematically wrong. Maybe he wasn't counting one side of the classroom, and that's why he was always missing students. Those are the 3 ways that we're going to be sort of considering error. Now we're going to switch over here, and we're going to do a section on error propagation. So if I have a bunch of measurements, they all have a bunch of plus or minuses, how do I carry the plus or minuses actually through equations, through math? So propagation. Propagate means sort of carried through. Just like with your sig fig stuff here, there's a separate rule for add and subtract, and there's a separate rule for multiply and divide. So let's go through them in turn. When we add and subtract, the rule is we're going to add absolute errors. All right. So I just emphasize for you here, I'm going to be operating on numbers. These numbers here happen to have plus or minuses. They happen to have absolute errors. What I'm telling you here is take those plus or minuses that each measurement has by itself and actually add them up. Now, if you're not careful, sometimes people, when they read this, they say, oh, obviously, if you add, you add. If you subtract, you subtract. No. If the operation is either add or subtract, it is always an add of absolute errors. Errors will steadily get bigger. If you ever make errors tinier, you better have good justification of why that is. So let me give you an example of the subtract case here. In chemistry here, we very commonly use a tool here called a burette. Our burettes here are 50 mil burettes. They can have a burette that's like 250 mils. It can be different sizes. What a burette does, there's a little stopcock valve. There's a little lever here that you can twist back and forth. And basically what it's supposed to do, you would fill this burette here up with liquid. And by opening and closing the valve here on the bottom, you can actually dispense that liquid here into another container. Burettes are very well calibrated. They're very well graduated and actually gives you the marking. Strangely enough, however, the burettes, I told you this is a 50 mil burette. Strangely enough, they put the 0 mark way up here, and they put the 50 mil mark down here. So now I want you to just imagine you were the experimenter here. You have the burette right now, it's empty. You have a beaker on the side here. You're ready to top up the burette. When you add, let's say, this amount of liquid, let's say we happen to be at the 10 mark, does that actually mean I actually added in 10 mils worth of liquid? Well, it couldn't be, because if the 50 mil mark is down here, we would have added some 40 with the additional end on the bottom. That's the exact case here. Although you're going to top up the burette, I don't really care what your starting reading is. What you're going to do is you're going to just take a reading. What does the burette say at this point? So let me just, I know you haven't seen a burette before, so let me just show it to you. We're going to have a 10 mil mark. We're going to have the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We're going to have it written like this. And what you're going to do is you're just going to load the burette. I just say something more than half. It doesn't matter exactly. And what's going to happen is your burette level is going to go down to something. Again, because the numbers are upside down, you just need to be careful how to read it. Well, because we're between the 10 and 11 mark, I know I'm going to call this the volume initial reading. My initial reading is going to be 10 point something. Well, this is going to be 0.1, 0.2, 0.3. Looks like that bottom meniscus here is after 0.2, not quite 0.3, so I'm going to guess 0.2. I'm going to summarize this a little bit more in the next lesson. We are allowed to guess one more digit. This value here, I might totally be wrong, but I'm still going to guess at it. It looks like it's maybe halfway, so 10.25. The units on a burette is going to be milliliters. And just in case I'm wrong here, let's give myself a little bit of buffer. Let's say it's 0.03. Right. The actual number that you assign for this plus or minus is up to you, up to your own confidence in reading it. Sometimes we are limited by how precise the device is. Sometimes, my glasses were foggy and I really couldn't see. Make this error bigger. That's totally fine. Right. So the actual size of the number is totally up to you. We'll talk about how you find that number in a later lesson. So that was the starting reading. We talked about here, you have not dumped in just 10, we've actually dumped into some 40. But here's the thing, we started off at this volume, I took a reading of what the burette said, I'm going to then dispense some solution. The liquid is going to fall out the outside here, it's going to go into the oil line on the bottom, and what I'm going to do is I'm going to take yet another reading, this volume, I'm going to call it volume final, and the volume final is going to be some number between 10 and 50. Maybe the marking, I might be between the 31 and the 32 tick mark. You do the same reading as we did earlier. Maybe it's 31.76. I wasn't as sure of this one here, 0.06 milliliters. So be it. Right? So I want to emphasize to you, burettes are a little strange. Not only are the numbers upside down, right, the zeros at the top and the 50s on the bottom, we actually didn't care how much volume we tossed in. We just took a reading to start. We took a reading to end. This is the finish. And all we're going to do is we're going to say, well, how much solution have you actually used? You just go big number minus small number. We still have some liquid left over, so I definitely haven't dropped in the entire 40 amount. But what we're going to do is just a simple subtraction. If I take 31.76, which it says right now, and we're reading it upside down, right? The 31 and 32, right? So 31.1, 0.2, that idea. 31.76 plus or minus 0.06. We're going to minus off our first reading. That difference should then give me how much solution that you've tossed in. 10.25 plus or minus 0.03, also in the milliliters. Notice my operator here is minus, so I'm undergoing this. We are not minusing absolute errors, we're actually going to add errors. Errors are going to get bigger. So for the math of it, we're going to follow our sig fig rules here. 31.76 minus 10.25. This one gives me here 21.51, no problem. And then all that's going to happen here is your absolute errors are just going to end up adding 0.06 plus 0.03. It's going to give me a 0.09. Do a double check at the end of the day. Does your error have one sig fig? Good. Error has one sig fig. If this one here had been plus or minus 0.12 or something, we would need to do extra math, but I kept this question fairly simple. Error has one sig fig, and make sure this one here that's unsure at the hundredths place, the second decimal place, make sure it lines up with the guess. I would actually do sig fig rules for the math here. The sig fig rules when you do a subtract is looking at decimal place, 2 decimal place, 2 decimal place. Yeah, I'm keeping that second decimal place. And fortunately, everything lines up. Everything's good, making sure you have the unit at the end. Let's see if you can spot where I would actually end up with this 0.09. If you actually take the first reading, this 31.76, the second reading, if I take the upper bound of this limit, right? I was saying this number here could be up or down 0.06 on either side. If I take the upper bound, that would be plus 0.06, so it would be a number like 31.82. And if I take the lower limit on this side here, the lower limit would be minus 0.03. That could be as far off as 10.25. I've now created the size of 0.09. And that's what that math tries to capture for you here. Let me just do a few what ifs. These numbers here worked out perfectly nicely. Let's say at this point here when I did the subtraction, let's say I ended up here 21.51, which I didn't, but let's say I ended up 21.51, 0.16 milliliters. Okay, just what if, right? What you would do out of the math, I'm assuming you did it correctly. I added up the absolute errors. I added up this buffer region. What you're going to do is you're going to round this. Error has to be one sig fig. Let's round it to 0.2. I can't leave it written 21.51 plus or minus 0.2 because then my guess and the uncertainty is in the second decimal place while my error says it may be 21.6, 21.7. That doesn't line up. So in that case there, although your sig fig rules allowed you to keep the extra decimal place, I say fine, I'm going to drop that one off and I'm going to round that to 21.5 plus or minus 0.2. And that way the one sig fig that your error has still lines up with the same position your measurement has with the units at the end. It's also possible that sometimes when you crunch through the math, sometimes we might get something like 21.51, this is just a what if again, 0.007. Right? Again, it doesn't line up. Maybe my sig fig rules only let me keep everything was 2 decimal place, so this final answer 2 decimal place, no problem. But the error seems to be too precise. The error tends to be like, well, I'm only going to be 517 or 503. It's actually off in the next position. In that case there, I'm going to make the error bigger. The error is one sig fig, it's fine, but it doesn't line up properly. I can't come along and suddenly go 21.510 because based on the sig fig rules, I could only keep this number. My only choice is to make the error bigger. So I'm going to keep it 21.51. I'm still guessing at the second decimal place, but let's make it a plus or minus 0.01. And again, the notion there is if it would have fit in actually 0.007, if you round the error bigger, it would definitely fit in 0.01. If you make the error bar smaller, you better have a good justification. And just the conclusion of there here, the uncertainty and the error must line up. Right? They have to match up. Second rule here, we're going to have second operation is multiply and divide. So that's some other common operations we can do to numbers here. When you multiply and divide, again, errors are going to add. But because the numbers are going to get big really fast and get small really fast here, the types of errors we're going to add are actually the relative errors. Are really those fractional errors, the how bad the plus or minus was on each measurement here. So let's just start off here. Let's imagine we had a table, and let's imagine I just gave you some readings here. Make this number here, totally make up a number. 65.72 plus or minus 0.04 centimeters. Let's make this side here a little bit shorter. Let's say 43.17 plus or minus 0.05. Right? So those two are the dimensions. I'm going to approximate it. It's a roughly rectangular table. Let's say the operation that I'm interested in here is to do the area. So area by definition is supposed to be length times width. So we're just going to crunch it through here. Length is supposed to be 65.72 plus or minus 0.04. The other side is 43.17 plus or minus 0.05. I know how to multiply the numbers, no problem. My final answer is still going to be these two multiplied. What we're trying to do in this propagation lesson is try to figure out, well, each of these numbers themselves actually had a plus or minus. How do we carry those plus or minuses through the problem? So here's how I'm going to do the problem. I'm going to still do the multiplication first. I still want the area, no matter how weird the calculations get later on. I'm still going to be taking 65.72 times 43.17. What I'm going to be adding and subtracting as I propagate the errors, I'm not just going to simply take 0.04, add 0.05. I'm going to take the how bad is 0.04 on 65.72. So 0.04 divided by 65.72. I'm going to add that to how bad is 0.05, the relative error on the second measurement. Basically, what's going to happen here, if I just typed in those parts, 0.04 divided by 65.72, this is telling me here, this is roughly a 0.06% off. 0.05 out of 43.17. These errors here are fairly tiny, which is good to see. This error here is roughly about 0.12% off. Not exactly a percent error. We're not talking that accuracy argument we just saw. But basically what I'm saying here is, because these measurements are fairly sizable, even if your rulers give you the precision of plus or minus 0.04, this one here is only 0.06% off. This one, how bad is it? Well, it's a slightly bigger absolute error. The measurement's a little bit tinier. The relative error is actually a little bit bigger. I'm going to be adding these relative errors. I'm going to say this was 0.06 off. This was 0.12 off. I'm expecting it to be roughly maybe 0.18% off, right? It's the relative errors that add up to both. And what's going to happen is I need to take this relative error, this 0.18%. I don't usually like a number like written as like, here's our measurement plus or minus 0.8%. I want to convert that back into absolute. So how I'm going to do that here is this part here, I'm going to still leave it in the decimal form, not actually multiply with the hundreds. This part here would actually amount to that 0.0018. So that's your 0.18% give or take. But that one there, unfortunately, is a percentage. Because it's a percentage, I want to take this percentage, now that the area has become a product, it's now become a bigger number. I'm going to just copy that out again. What is 0.18% on my product, which I haven't yet typed in yet? So I would usually just show my work like that. And that part here, this part, just helps us converts back to absolute error. We've already done the addition of relative errors. That was 0.06 off, that was 0.12 off. I'm about 0.18 off. But then what is a 0.18 off out of the actual area? So I just rewrite the area term here. The sig fig rule is followed by itself, and the error rule is followed by itself. So let's go 65.72 times 43.17. Based on the sig fig rules, this is a 4 sig fig number, this is a 4 sig fig number. Even though the calculator spits out 2837.1324, we would need to round it to a 4 sig fig number. I'm just going to circle where it's guessed. On the other side here, this guy is the mess. Let me just show you that one middle step here, 0.0018. That already is the percent error that we want, but I want to convert it back to absolute error. What if I took that 0.18% and what if I multiplied it by 2837.1324? I'm going to tell you can be a little bit sloppy with error. I want to just basically don't have any rounding issues going through it. Take the entire number, multiply point, and let me actually retype that whole relative error in. Right, I want to keep all the digits if I can. Double check my numbers, and I'm getting, when this is back into absolute error, we're talking about a 5.0128. The reason why you can be sloppy with error is once I have the final number, I would round this to 1 sig fig anyways. Round to 1 sig fig. When I do that, 5.0128, I'm going to round to 5. And then I'm just going to check it against my measurement here. I expected it to be 2837. I would round to that 7. My error when I had 1 sig fig is in the ones position. Even though my measurement has 4 digits, we can still round. The guess position is actually also in the ones position. So this is perfectly fine. And the final unit is going to be centimeters squared. If it wasn't matched up, we would do that same what if practice we had earlier. Either round the sig figs or round the error so that they line up. Again, I want to emphasize that there, what we're saying is not if error is 1 sig fig, your measurement has to be 1 sig fig. In fact, this measurement here actually has 4 sig fig. It's just the guess, the one that's farthest to the right, the one that I'm eyeballing, the one that might be wrong. That spot has to line up with the spot on the other side. I'll leave mixed calculations for the next lesson here. I want to finish off with one more operation. That operation here is going to be taking averages. So especially when I do multiple trials, right, I expect it to minimize some of the random errors, sometimes high, sometimes low. What I'm going to do is I'm going to show you how you propagate errors through a average. So let's go back to our experiment here. Let's say I have a grad cylinder, I have the 10 mark, right? I'm going to go around and I'm going to just ask a few people, well, how much is in there, right? So, I'm going to make a few trials of this here. So remember the wording trial means you're going to repeat the exact same experiment a couple of times. When I asked the first person, they said 4 plus or minus 1. I asked the person again, they say 5 plus or minus 2. I ask the person again, they go back to 4 plus or minus, just making the numbers different. So let's say 3. Right? Again, I'm not surprised that there is minor fluctuations. It isn't a very imprecise tool here. So this is 3 of the same reading on the same graduated cylinder. There's 2 ways these averages here can be dealt with here. An average, if absolute errors are given for all measurements, so that's the case here. So not only has they told me, oh, I think it's about 4, about 5, about 4, they've given me the plus or minus each time they came. What we're going to end up doing is we're going to end up just averaging. Average the errors. And I'll show you mathematically what we do here. Well, let's just crunch the numbers first. When you take an average, you add them up, divide it by. So I add up 3 numbers, I divide by 3. That's just operating on the measurements. What I'm asking you to do here is the same thing happens to the plus or minus. The first one was plus or minus 1, the second one was 2, the third one was 3, and then you divide by 3, I end up averaging. Why does that work? Well, an average is actually, I punch through plus first. If you look back at the plus rule says take all the absolute errors, just add them up. Right? That was add or subtract. The absolute errors just gradually get bigger. Great. Then what we do is we end up scaling it down by 3. The question here is, how sure am I this is 3? Well, this 3 came to be because I actually have 3 different measurements I'm actually averaging over. This one here is what's referred to as an exact number, sometimes also called a pure number. There's actually no relative error to there. So this right here doesn't contribute any extra error. We're going to prove this to you in the next class. Basically, if this gets scaled down by 3, your error also gets scaled down by 3. So 4 plus 5 plus 4 divided by 3, I get 10.33 divided by 3, sorry, 3.44. Right. Plus or minus, this average here would be 2. Based on my sig fig rules here, unfortunately my measurements were only 1 sig fig. I'm only allowed to keep that one position. And if I check the errors position in the ones position as well, I would then write out my final answer. On average then, you said 3 plus or minus 2 milliliters. Is that right? Oh, sorry, 4.33. No, it looked a little weird. Sorry, my bad. So 4.33. I knew it should have been somewhere between the 4s and the 5s there. So 4 plus or minus 2, rounded to 1 sig fig here. That looks better. And therefore, the average is putting us somewhere in the middle. It would have minimized some of those errors up and down. And then we now give ourselves room up or down. It could be as off as 6, as low as 2. You notice it doesn't cover everything. This last error here could have actually been up to 7, and that one could have actually been up to 7, but that's the way we do it with absolute errors. Let me just finish off here. What if no errors are given? So if no errors are given, we still have this belief the more measurements you take, it'll minimize some of the random errors. What we're going to do for the error is we're going to associate what's called plus or minus half the range. So let's say we were looking at that grad cylinder again. This time, let's say it is 100. Right. I ask a few people around, and they say, oh, I think 41. I think 37, 46, 39, give or take. So I asked 5 different people, and they didn't do it very detailed. When they said 41, they didn't give me right away a plus or minus on each of these numbers. So you notice I don't really have the plus or minus. In some sense, I actually can't do the error. But again, my belief is because I asked 5 different people, hopefully some of the ones that are on the high side will cancel the ones that are on the low side. The average should get me somewhere in the middle. So no problem with adding the other ones. 41, 37, 46. I'm adding 3 numbers. I'm going to be scaling it down by a pure 5. The question is, how much should I associate for the plus or minus? Again, this is just an approximation. There's no one right way of doing error. Just make sure you're consistent with your trials here. What you're going to do is you're going to look through your set of numbers. None of them have plus or minus. Figure out which is biggest. So the maximum in this case here is 46. Figure out which is smallest. The minimum, which is 37. What I'm going to get you to do is I can get you to order them. 37, 39, 40, 41, and a 46. So I have my max and my min. What I'm going to get you to do is I'm going to take your max minus your min. That's going to be called your range. In this case here, if I take 46 minus my 37, that gives me a relative spread of these numbers here. The relative spread is 9. I know what the average is going to do. The average is going to put me somewhere in the middle. Now that I have a range of plus or minus 9, I'm only going to associate. I don't need a full plus 9 and a full minus 9 because I'm going to be roughly in the middle anyways. Let's take 9. Let's do half the range. Half the range here would be 4.5. Again, there's no reason to be too precise there. Let's say it's about 5. If I'm already in the middle and I only let myself be wrong, sort of up 5 or down 5, that should have been able to capture some of those fringes, some of those extremes there. So let's finish this question off here. 41, 37, 46, 39, and 40. When you average them, the value they put you in the middle is 40.6. I would round that to 41 based on our suffix. So again, as expected, 41 puts me in the middle. If I associate half the range, which you said was about 5, if I write my final answer as 41 plus or minus 5, let's see how that did. So 41 is somewhere in the middle. That's awesome. If I have a plus 5, I can capture the 46. 41 minus 5, I can actually capture the 30, the minimum. I can actually go past the minimum as well. Again, this is not a perfect system. Realistically, they could have said 40 plus or minus 60. I wouldn't be able to capture that. But seeing as I had asked a few people, taking 5 measurements makes me believe in this measurement more. So if I'm not given all the errors, I calculate this range. I calculate how far spread out my numbers are. I know my average puts me somewhere in the middle, and I associate myself half wrong going up, half wrong going down, and that should cover the entire distance. We'll do a little bit more practice in tomorrow's lesson, but at least get a little bit of practice with propagating through errors. If you have any questions, just let me know. Thanks, guys.